previously we talked about a formal definition for computation for a deterministic finite automaton, or DFA. So we want to use this definition to help us prove the correctness of a DFA. So what does that mean? Let's talk about that. So proving a DFA is correct. So, helpful exercise to go through, very important, because you want to make sure what you have is correct, right? So what does that mean to be correct? So suppose we want to prove that some DFA M recognizes a language L. Seems like a pretty sensible thing to try to do. You want to make sure your DFA is correct, right? So to prove this claim, as we previously suggested, it has to be that for every input string W, it has to be that W is in the language of the DFA, which we described last time, if and only if W is in language L. So that's my desired language. I would like to make sure that my DFA always accepts strings that belong to this language, and whenever the DFA does not accept the string, it better not be in this language. That's what this says. The if and only if just simply means if this is true, then this is true. If this is false, then this has to be false. That's actually something helpful we'll actually talk about today. The if and only if is a very strong claim in mathematics. So given the inductive way we defined computation for a DFA, it is common to prove correctness via mathematical induction. So just to be clear, correctness simply means that for every one of the input strings, if W gets accepted by that DFA, it belongs to the desired language that you would like to establish, is in fact the one you designed the DFA for. Likewise, whenever that rejects, it better not be in this language. That's all we're saying. Just in the same breath as if I was talking about deciding if some array had a value X in it. So I would like to know if it is an X or not an X. So if you design an algorithm for that, it better be that for any finite array and any X, it should be able to tell me if X is in the array or X isn't in the array. If it does sometimes tell me that X is in the array when it isn't, then most certainly it's not working correctly, right? I mean that in the same way, kind of like this. In fact, it's the same notion. So, a common technique as you may have seen if you studied algorithms before, that's okay if you have not seen a whole lot about algorithms. A common technique is to use invariants. For how how the DFA processes the string. And one thing that's really important to note is that this may involve the states. So it may involve the states of the DFA. So normally when you're performing induction, it's typical to see you perform induction on the string, so on the length of the string. Because every string in the DFA will have some length. So it's typical So it's typically done on the length of the string W. So you consider any string of length of a given length. And every string is a finite string, so you just enumerate all of them up to some desirable you start at some length, depending on what you're claiming, all the way up to any given length that is necessary for your claim. So let's do an example applying this idea. Last time I'd shown you a DFA that we claimed accepts strings with an odd number of zeros in them. So I'm just going to remind you what that looked like. And we made a claim about it actually when we did. I'm just going to put the loops down here. So we claimed previously that this DFA, and I'm going to call it M odd. This is the transition diagram of M odd. So the claim is that this accepts only strings with an odd number of zeros. Which of course, the set of all binary strings with an odd number of zeros in them, that is defined by a language. And I need to establish that the language of M odd is in fact that same language. So that's how I would prove the correctness of this DFA. Now, when we were designing this DFA, which has two states, when we came up with it, we thought about some ways that we could kind of assign roles to each one of these. So I want you to notice something, and this is how we're going to take advantage of the structure of this DFA. We're going to try to establish what we call an invariant. So this is a property such that during the execution or processing of the input string, it has this property at every stage during the DFA's execution. I was about to say algorithm, but remember, it is technically computing something, and it is a process. It's just over a DFA. So it's still carrying out a process, an algorithm. It's just that we're using it in a much more limited scope for this model of computation. So the DFA is processing the string. And what did we notice? So notice that whenever we're in Q0, there's an even number of zeros. And whenever we're in Q1 in M odd, there's an odd number of zeros. So do you notice that all you do whenever you read a zero, you go back and forth. So if you're in this state, you go to Q0. Whenever you read a zero, you go back to Q1. And we want the case when there's an odd number of zeros. So what I would like to do, and I must stress that you don't have to do this, but I'm trying to get you familiar with this idea of providing a strong observation about what exactly this DFA is doing because of what I told you previously about a DFA. A DFA only remembers, we're assigning a property to it that it can remember things, but we know that this thing processes based on the present state it is in and when it reads a symbol, right? It doesn't have any other features. So it could be possible when we perform mathematical induction, because remember, the way we define computation for a DFA was based on the state you're in and the current symbol that you are going to be examining. It's going to be quite natural that sometimes it's going to be that we could potentially have it where the DFA transitions into the accepting or final state upon reading a symbol. And it may be a little tricky to prove using induction that the DFA actually, in fact, will be in the appropriate state that we prescribed in our design. So we designed this DFA specifically so it would have this behavior. So we would like to make sure we could prove that is in fact the case. And if we do, at all stages we have this property, then most certainly we get this one for free, right? Because Q1 is the accepting state, and that's exactly what I want to prove. If I could prove that both of these properties are in play at every one point of execution for the DFA when I read a string, then most certainly we've proven the claim, right? All we have to do is just point out and say, hey, look, guys, M-odd's final state, it only has one of them. It is Q1, and the invariant would say that, hey, look, it has an odd number of zeros. That's exactly what we're trying to claim about this DFA, right? But sometimes it can be quite tricky to accomplish this induction step. In this case, you don't actually have to do this. I'll include in my notes a full proof where you don't actually prove both of these invariants. So we don't actually have to prove that both of these are in play. It's actually, in this special case, if you prove this, you also get this for free. In fact, so keep in mind that, just keep in the back of your mind that when we have our proof, it'll be the case that if we establish this, it's the same as me saying this whenever this isn't satisfied, right? This is actually a special property this DFA actually has. But I'm trying to lay out a much more general way of thinking about invariance in a DFA. Because you got to think a little bit ahead, everybody, because remember, we're going to perform induction on the length of the string that we have. So remember, in the inductive part of the definition, we had it where we decompose the string like this, where this is the rest of the string and then this is its last symbol. What I would like to do is use the induction hypothesis on X, and then I append A. At least that's one way you can go about it, right? But I need to make sure that X has a property that I'm aware of and I know which state it's in. If I can do that, then I can apply induction correctly. If I cannot do this, I don't have enough assumptions in play for my induction hypothesis to correctly apply induction. So I know it's a little bit of much to throw at first, but I'm hoping you'll appreciate this little detail when we actually talk about the induction proof. In this specific case, it's not required to have both of these invariants for our claim, because if you had one of these, then you get both of them. But in many DFAs, it will not be like that at all. But I must also stress that you can usually think about a much more general process for doing this approach, which I'm going to show you. This is one way of going about it. But most certainly, you'll find that there's other ways that are much more specialized, as you could in this example. As stated, I will include an alternative proof that only uses this invariant, and then only establishing that invariant. But I'm going to try claiming that there's both of these in play. So here's the claim. So if I prove this, the correctness of the DFA will not be very hard to prove. So so this is a lemma. So I'm going to use this to help me prove the correctness of DFA M-odd. Given DFA M-odd, so given DFA M-odd and any binary string, I'm going to use the extended transition function to help me here. So the first thing I'm saying is that delta hat Q0W. So if I read string W and I start at the start state, and if I land up in Q0, it has to be if and only if. I'm going to abbreviate if and only if as IFF. If and only if W has an even number of zeros. Likewise, my other claim is that delta hat Q0W is equal to Q1, meaning that upon processing string W starting at Q0, and I land up in Q1, this happens if and only if W has an odd number of zeros. So please take note that you try to design the DFA such that these two categories are separate from each other. Otherwise, it becomes very difficult. In fact, it's going to be maybe too challenging to be able to tell between one state and another state. This is why when you design the DFA, try to make it so that the strings map to some state. Almost look like, so if I have an odd number of zeros, it better be that I better be in state Q1. Whenever there's an even number of zeros, I would like it to be in Q0. I don't want it where it's like crisscrossing, where sometimes it's odd, sometimes it's even. It's going to be, it might make it too difficult to prove a claim using induction here, if that's the case. So let's prove the claim using mathematical induction now. So the game plan is we're going to use mathematical induction on the length of the string. And we start off with the empty string, because that's the shortest string. Now, oftentimes when you have invariants laid out like this, it may be the case that an empty string will never reach to one of these states. So oftentimes when you have many of these so-called invariants, what happens is sometimes they never become applicable. So they become vacuously true. That simply means that it never really meets the conditions of that statement. So by default, it's just inapplicable. It just doesn't matter. So if you have invariants that you just never really can establish the truth of their claim, you may not go up another length. So you might try, when we start with length 0, you may go length 1, then maybe like 2 if needed. Depends how strong of an induction claim you need. In our cases, we just need one base case, but that doesn't mean if you have a much more sophisticated DFA that you might need more. Either way, you can always add more base steps. There's nothing wrong with that. If you need to convince the reader with more base steps, that's okay. But sometimes the induction requires that you have it where you can presume that there's, say, maybe a couple smaller cases that you can actually invoke the induction hypothesis on. Those are cases where you might need more base steps. Here we always just need one for our examples, but that may not be the case all the time, just to be very clear. So we prove, so whenever I refer to the statement, I'm talking about the lemma. This is just me being less verbose than I need to be. To prove the statement, we prove the statement via mathematical induction. So I'm going to be using weak induction to do this. Via mathematical induction on the length of the input string W. So we're going to do our base step. Base step. We're going to start off when the length of the string is 0. So this is an empty string. This one's not going to be terribly interesting, right? Because if I start off in Q0 and I read the empty string, I'm going to stay in Q0. But how many zeros are in the empty string? There's none, right? So think about what parity that has. Is that even or odd? So the empty string epsilon contains an even number, right? An even number of zeros. So to prove this, I have to show that this is still in Q0. So we must show that M odd is in state Q0, right? Because our claim is that it's an if and only if claim, right? So to satisfy our two invariants, it has to be that if there's an odd number of zeros, it has to be in Q1, but we know that if it's in Q0, that would naturally match the invariant that we have in place, because, like I said, this is a little verbose, these invariants, because one of them actually implies the other one, because we only have two possible states. That's actually how the alternative proof plays out. But just because this is the first time we're doing this, I'm going to work it out carefully with you. Well, let's use the extended transition function. Well, delta hat of Q0 epsilon is equal to Q0. Right? I stay in Q0. So this is proving. So this proving the statement for the case when the length of the strings are all 0. Right? Piece of cake, right? This definitely works to satisfy both conditions, right? Both our invariants are satisfied because it's not in Q1, implying it doesn't have, so if it isn't in Q1, then it has to have not an odd number of zeros, right? Which this has an even number, right? It's only because of our hindsight that we know that there's only even or odd numbers of zeros, right? So since I have two states, it just works out really nice and easy for us, and it coincides on both of them. I just wrote this out intentionally to strengthen our induction hypothesis. But again, like I said, this is just meant to make it easier for us to prove the claim. We don't actually need both in this specific case. But in other cases, when we strengthen the induction hypothesis like this, it might actually be necessary to carry out the induction. But sometimes this technique that I'm going to show you can be a little verbose, so I'm just warning you in advance about that. So the induction step. So we're going to fix some n greater or equal to 0. So we're going to fix some integer n greater or equal to 0, right? Because I proved it up to the statement when it was 0. So then we're going to let the length of the string be equal to n plus 1, assuming the statement for strings all of length n holds. So I'm saying that the invariant holds, or both of those invariants, which technically the same one, but if both invariants hold for all strings of length n. So my job now is to show you how you tack on another symbol onto the right, in our proof at least, to make this work. So consider any string w is equal to w, so w is equal to xa, such that a is the last symbol of w. So I've just decomposed w such that I just put the last symbol off to the right, okay? So this is everything but a. So this is just w less the last symbol, just to be clear. I should be very careful when I specify this. So just be very clear. X is just w, where I just take off the last one, just like when I talk about a string like cat. What x is ca, a is t. Almost look at it like I'm appending to x the last symbol, like if I was reading the next symbol. That's the intuition for how we're going about this. And if you can get that, then you can see how we can use the extended transition function to our benefit here. So to continue our setup, we show the statement also holds for string W. So we got to show that it holds for string W, which has length n plus 1. Now that we have this in place, the setup here, what can we say about string X? String X. What's its length? Its length is n. It has n symbols in it. So string X has length n. So string X has length n. And just to really kind of hammer this in, I'm just using a sledgehammer at this stage. I don't need this, but it most certainly was easy enough for us to talk about. And has either an even number of zeros or an odd number of zeros. Right? So what can we do? I apply the induction hypothesis on X, right? That's what I'm doing. So by the induction hypothesis, either, there's no other choices here for X, either delta hat Q0X, so this is processing X starting at Q0. I need a comma in there. There's a comma between Q0 and X there, if you're wondering. Is equal to Q0 or delta hat Q0X is equal to Q1, respectively. That's what we can say. Why? Because whenever the string has an even number of zeros, what happens? Even number of zeros, it's in Q0 for X. That's what the induction hypothesis would say. And when it has an odd number of zeros, X has to be in Q1. That's what it says. That's what the induction hypothesis tells us. So what's all we have to do now is as follows. So check this out now. And this is what is really nice and slick about this inductive, this definition. You can tell my excitement, okay? So we had two different scenarios. Either we end up in Q0 or Q1. We end up in Q0 if we have an even number of zeros in X. We end up in Q1 if there's an odd number of zeros in X. So in the two possible situations, it's going to be either W is equal to X0 or W is going to be equal to X1. Right? Those are the only two possibilities that can happen for W at this stage. So my job now is to exhaust 4 cases for you based on the way I've set up this proof. So now, whenever I get, if it were X is, I read X and I'm in Q0, I have to read a 0, read a 1. Whenever I'm in Q1, I have to read a 0, then a 1. I just use the extended transition function. So now we're going to just lay out each one of the cases for you. So there's going to be 2 first that are going to involve when X has an even number of zeros, then 2 that are going to be for when X has an odd number. So I'm going to break them into the 2 groupings, each with their own 2 cases. So 4 in total. So the first one is going to be delta hat Q0 on X is equal to Q0 and A is equal to 0. So that's the first one. And then there's going to be another possibility, right? We're going to have another one. This is the only other possibility that can happen for when I end up in Q0 upon reading X, is I read a 1. So we just need to make sure that, remember, in both of these cases, X has an even number of zeros, right? That's the layout for these two cases. The other two remaining cases are when we have an odd number of zeros in X. So now what I need to do is I need to work out each one of them and make sure. So for example, just as a quick example, when I read another 0 like this, and I already had in X an even number of zeros, then it becomes an odd number of zeros, correct? So notice here that this particular situation is when I could have it go back to Q1. Or if it never was a Q1, it's going to go to Q1, which is exactly what you want to have happen with the invariant. So in this case, W has an odd number of zeros, right? Because X had an even number. Has an odd number of zeros. And now let's just work out the extended transition function. Delta hat of Q0W is equal to delta of delta hat. So I just apply the recursive, I could say recursive or inductive part of the definition. So delta hat of Q0X upon reading A. But in this case, A is equal to 0, right? So this is just Q0 upon reading 0, which this is equal to Q1. That's exactly what you'd expect to happen, right? Odd number of zeros lands up in Q1. Exactly what you want. Next, so let me just number these. 1, 2. So in the second case, we're going to have it so I'm going to say as expected because I'm just going to be confident at this moment. As expected, W has an even number of zeros. And now let's just apply the extended transition function. Delta hat Q0W is equal to delta of delta hat of Q0X upon reading a 1, right? Well, what is that? What's that? What's that thing over there? That's going to end up being, well, what should you expect to happen if I read another 1? Well, does it go to the other state? No, it just stays in the same state. But this is just equal to Q0, which is what you'd expect to happen, right? So that's our first two cases. So that covers any situation for which you're in Q0 already. Now we got to talk about the cases for which you were in Q1, meaning that X had an odd number of zeros. So we're going to have 3 and then 4. So this is when delta hat Q0X is equal to Q1 and A is equal to the symbol 0. And we have delta hat Q0X is equal to Q1 and A is equal to 1. Right? These are all 4 possibilities. We're just breaking it into cases for the induction step. So this is just when X has an odd number of zeros. So now let's work out these ones. So here the string W. How many, what would happen if I have another 0 on W from X? Well, I had an odd number before, but now it's even, right? It's an even number now. here the string W has an even number of zeros, and delta hat Q0W is equal to delta of delta hat Q0X upon reading, well, in our case, A is 0. So this right here, we already know this is going to end up being Q1. So this is just Q1 right here. And I'm reading a 0, and that leaves me in Q0, which is exactly what you'd expect to happen if we want to ensure our invariants are in place, both of them. Then lastly, we have our last case here. So we have string W. We have string W contains an odd number, right? Because remember, it has a 1 on the end instead of a 0, so it's just dictated entirely by X. String W contains an odd number of zeros. And now let's just work out the extended transition function. Delta hat and delta hat of Q0W is equal to delta of delta hat Q0X, and upon reading a 1, right? This is going to be just Q1, right? When I read a 1 and I'm in Q1, I stay in Q1, right? And that's exactly what you'd expect to happen. And now we've considered all 4 possibilities that can happen. Thus, we've completed the induction step. So let me just make sure I say that. It's very important to say that because we're not quite done the reasoning for the induction step. So, because we've covered all possibilities. Thus the statement follows for when the length of the string W is equal to n plus 1, completing the induction step. Completing the induction step. Now we get to our goodies. Now that I have this in place, let's proceed now to wrap it all in a nice bow, because now I have my 2 key ingredients. Now I can use the principle of mathematical induction. Let's now invoke the principle of mathematical induction. Remember, you got to do that. It's kind of important. Otherwise, you just gave the steps needed, but not the reasoning to conclude what you need to conclude. Therefore, by the principle of mathematical induction, the statement, as in the lemma, the statement holds for all lengths of strings. And we're done the proof. So we're not quite done yet. There was something else we also had to do that I haven't explicitly stated yet, right? I did before we started, but most certainly I did not actually do it yet. What was it? That lemma says that, it says what? The lemma originally had over there, it said that we're in Q1, so m odd is in state Q1 upon processing string W, if and only if W has an odd number of zeros, right? So that is the only final or accepting state of the DFA, so now let's invoke that. So observe. So now we finished the proof of the lemma. This is technically the proof for the correctness of the DFA now, but I'm just going to put it before I place the statement for the theorem. But if you wanted to make this like theorem proof style, you would just put what I'm going to say here inside of your proof. Okay? Observe that state Q2 is the only final state. It's the only final state of m odd and any string W, accepted by M odd satisfies what? What does it satisfy? It satisfies that the state of transition function delta hat, when I start at Q0 and I read W, it has to land up in Q1, right? That's what it means to accept when we talk about M odd, right? So this is the key observation we need to make this all work. So now I just invoke the lemma, right? So now we just invoke the lemma. So by our lemma, input string W is accepted by M odd if and only if W contains an odd number of zeros as desired. So this brings us to this theorem. So now we got a theorem, because this tells us this reasoning is what gives us the correctness of our DFA. So the language of M odd is equal to the set of all binary strings such that W has an odd number of zeros. Boom, there we go. So a couple comments. So I alluded earlier to the idea that there's an alternative proof. So please if you go back to the lemma, you'll notice if you're familiar with logic, you would understand that one of the invariants actually implies the other one. Why? Because there's only two states. So not being in Q1 means that you're in Q0. And any string that doesn't have an odd number of zeros must have an even number of zeros, correct? So in a very special way, we can specialize this argument. And in fact, the proof becomes a little shorter. So for example, you should be able to get away with only needing, I believe, let me just quickly just take a quick peek. I just always like to talk about this. Let's see. Yeah, you only need two cases. Rather than four, you just need two. You only need the ones that are relevant for that invariant, just the one of the two, which is only just really one. Because the main observation is that if you use the induction hypothesis, it says whenever you're not in Q1, you have to not have an odd number of zeros. But we know from a number theoretic standpoint, that means you have an even number of zeros. And the only other state is Q0, that isn't Q1, right? So in the notes, I will include an additional example showing how you can refine this proof down to two cases. So this brings me to talking about a framework for which we can talk about proving the correctness of a DFA. This, like I said, this is one way you can go about this, and I tried to keep it so that this follows the same type of layout, even if I didn't need both invariants. But notice that I provided an invariant for each one of the states. Did you notice that? I had two states, so I had two invariants. I could even have one that characterizes a bunch of states. But the point is that I take each one of the states and I say, hey, look, this is what you're about. You have some property, an invariant. And this helps us to prove induction claims a little easier sometimes. Why? Because, like I said, the DFA only remembers where you currently are and what you're going to read next, okay? And when you do that induction step where you have your string, when you read the next symbol, that means you're going to decompose W into two parts. A string of length n and your next symbol you're going to read, right? And we use the inductive part of the definition of computation for the DFA via extended transition function, we need some way of knowing what's going on with the string x. Because it could be the case that it actually doesn't satisfy the induction hypothesis if we don't consider a possible state for which it could transition into the accepting state, potentially, right? It could be the case that maybe there's some undesirable state out there that we didn't account for. So this brings me to talking about a framework for which we can prove the correctness of DFAs. So using state invariants. So what I described, those two invariants, even though I didn't need them in that very special example, the point is that I described a role that I assigned each one of the states, right? And it preserves that property during the processing of the input string. So we call those state invariants. So each one is an invariant. They're all based on a state. So when you're in this state, there's some property that it holds. So designing effective DFAs also means that you can just tell me something about when it's in that state, what is it doing? Like what exactly is it supposed to do in that state? So that's something to keep in the back of your mind when you're designing a DFA. And it's not just me just saying, giving you advice. It may actually be very helpful for proving its correctness. Just like when you describe an algorithm to somebody, it may not be the shortest description of the algorithm, but most certainly it's easy to pick up a property that it may have. And then once you know the correctness of that algorithm, you may specialize it a little further, and it may make it easier to prove that claim. Or equivalently, and I'll mention this in a moment, is that if you prove the correctness of a DFA, there's a way to transform these DFAs in a way such that you can refine them further. But since that process is correct, then you can ensure that your DFA is still correct. So just keep that in the back of your mind. So using state invariants. So while possibly verbose, so like I said, you could, for a specific DFA, there might be special properties it has. Just like when you talk about an algorithm, you're attempting to solve a problem, it may have very special properties for that given problem, and the way you write out the algorithm that you can take advantage of to exploit to come up with an invariant or some property that allows you to basically spill out the correctness of the algorithm. Same thing here, right? But this, you could think of this as a framework to do this. Well, possibly verbose, the way we proved some DFA M and some language L satisfies L of M, referring to the language of DFA M, and the desired language L that I would like it to be designed for above. So above, referring to our previous claim, was using the following argument. So I'm just going to lay out the game plan that I described earlier, but do it explicitly now. Was using the following argument. So we use this argument. So this is the game plan. I always like to refer to these things as game plans. So let me walk you through what we did. So the first thing we did was we identified. So you identify state invariants. So that's the first thing. So it's identify state invariants. For every state Q in the set of states, we're going to determine some language. Determine a language, I'll just call it LQ, like the language of that state. Language LQ, so that whenever M transitions into state Q, upon reading W, upon reading string W, W belongs to LQ. So just to be a bit more precise about what I'm saying, that is W is in LQ if and only if delta hat Q0 W is equal to Q. So this is what people call, so this is called a state invariant. So that's what a state invariant is called. So you can imagine, just like I told you when we were designing DFAs, you can think about, at least if you want to adopt this type of argument, you can think of each one of the states having like a role. And whenever it transitions into that state, it has to have some property. So when any string that's in that state has to have this specific property. And that property is dictated by this language. So for example, in our case over there, we had it where we had Q0 and Q1. Q0 is whenever you're in Q0, whatever string it is, all of those ones have an even number of zeros, right? Whenever it's in Q1, it would have an odd number of zeros. So those are two different languages, right? So whichever one you're looking at, so this is how you might formalize that. 2, upon realizing or observing this, so that might take some time to think about this carefully. So prove the state invariance. So now you can just prove the state invariance. So prove the state invariance. My m's and n's are sort of melting into each other at the moment. Prove the state invariance. So usually you'd want to use induction, but I'll write it here, but just be aware that whatever technique you need to use or want to use, that as long as it's correct, of course, you might do that, but you'll find that it typically falls into this. Prove via induction on the length of the string that for all input strings W and all states Q in Q, so the set of states, it has to be the delta hat Q0 W equals Q if and only if W is in LQ, as I stated. So is it just formalizing what I had stated just a moment ago? So lastly, what are you going to do now? So what did we do when we did our example? Well, I just put my finger and I said, okay, well, which ones are the final states? So I said, okay, there's just this one, right? We had Q1. So what exactly is the DFA? What is the DFA accepting and rejecting upon? Well, it depends on which final states you have, right? So even though you have all these other state invariants, the ones that matter, the LQs that tell us about which ones get accepted, are the ones that are the final states. So now we just employ the definition of L of M. So just simply consider, consider all final states, states F, now prove that the desired language I would like to prove my DFA accepts is equal to the union of all of my languages over the final states. So I go over each one of my LQs, I put them all into one big bin, And so I go over all of the final states. I look at that invariant, and I take that language and I put it into one potentially larger set. And my hope is that that's equal to L. The one I want to prove is equal to L of M. Because anyone that is L of M looks like this, right? So just a few kind of things I really want to touch upon, just based on things I've talked about already. So just some remarks. So first, so proving the correctness of a DFA does not require using state invariants, as I described over there, right? So as discussed, just as I mentioned, there's a way to specialize that DFA's argument such that there's only really an invariant that gets held at every point. There isn't one, like you could characterize it as one for each one of the states, but when I actually carry out this alternative proof, I only really care about what's going on with Q1. Because anything else that's not Q1 actually has a very clear characterization. But that's just because of that DFA. So my point is that not every proof you're going to run into looks exactly like this, but most certainly you can craft them like this. That's the first remark I have. As discussed. So why you might use state invariants. State invariants is to do the following. So just some big highlighting points, just some discussion I have for you. So one, determine the form of W is equal to XA, as we have in the induction proof, as in the inductive part of the definition of computing for a DFA via the extended transition function. Or equivalently, it could be that W is equal to AX, depending on how you define the extended transition function. And the state it may be in during the induction step. So you got to imagine the induction step is like you're executing the process, you're processing the string. So this setup helps you think about how to carry out this. So carefully, when you come up with the state invariant, sometimes you want to keep this in mind, that you're going to eventually need to decompose the string kind of like this or like that, depending on how you define the extended transition function, based on how you want to use induction. But my point is that this helps you think about this process when you use state invariants. So it gives purpose, I'll use quotation mark because it's just more of an abstract concept. It gives purpose to a state when designing the DFA. Because you don't want to, usually it's not a wise idea, just like when you write up an algorithm. It's usually not wise to have it so that the algorithm can be potentially doing different things at the same time. Not literally at the same time, but as in I give you two inputs. It may be the case that it's like there's two instances that might actually be running the same part of your algorithm, but they may be doing it for very different but incidental reasons. So you may have like one case a collapse, like the way you describe the algorithm collapses on two cases, but the way it gets used in the algorithm actually might be the exact same process with like a branching, like an if statement or something like that, for example. Something like that might happen with a DFA, You try to avoid this if you want to use state invariants, but it also encourages you to think about each one of the states when you're thinking about designing it, describing what each state is supposed to be doing. Like, what is it for? Think carefully about when you do this, is that you want to think about the purpose it might have, the purpose it may have, may help you characterize a state invariant. So sometimes it's actually a much stronger statement you can make when you do this. So then it is more about designing, I'll put that in quotes, it's more about designing it so each string, quote unquote, fits an invariant. You don't want to have it where one string just sort of maps onto multiple invariants. You want to avoid having more than one. Each string fits an invariant. I should be clear. Because you don't want to have it where it has it satisfies 3 of them, then you aren't sure which state it might be in, and then you have to exhaust those possibilities potentially, or it may be too hard to tell using induction what's going on, depending on what your DFA is like. Either way, it's going to give you a much harder time. Now, as an aside, as I mentioned, when you're thinking about it like this when you're designing a DFA, just as an aside, if this is something that interests people, I can definitely cover it at some point, is there do exist algorithms to, I'll say, instead of 2, I'll say that can minimize the number of states of a DFA, So please keep this in mind, is that in practice, if you were to pick this up in a more practical utilitarian way, you design the DFA, it may be the case that you have a very coherent, easy to understand, easy to prove claims about DFA. So it may be the case that it has a minimum number of states that you could design it for. So what I'm saying is you minimize the number of states, the simpler the design may get. However, it may become incoherent exactly how and why it works, unless you actually carefully study it, which you, of course, can. But the thing I'm saying is that if there exists an algorithm that correctly can take your DFA and construct another DFA with a minimum number of states possible from your design, it may be more important to focus on designing a DFA in a way that you can prove that it is correct, more so than focusing on the goal of having one with the smallest number of states. That in itself may not be the best place for starting, but getting a minimum number of states to simplify the size of the DFA may be a goal after coming up with a DFA that works correctly. But regardless, there does exist a process for which you can minimize the number of states of a DFA.